Okay, let's go ahead and begin. It is getting close to 1:02. And I think we have most everyone here. Okay, hello and welcome everyone to the third in series of the ASCE Spring Seminar. Today our speaker is Dan Fitzwilliam. Really great. Dan has been designing bridges around the world for 24 years. He graduated from California State Polytechnic University, Pomona, and continued to get his master's degree in civil engineering from University of Florida. In addition to his work on all types and sizes of hybrid bridges, Dan has become a specialist in the design and construction of unique pedestrian bridges. For the last 15 years, he has worked for CMC International in the San Diego office. His current role is managing the Southern California branch of Dublin Link International's complex bridge department. So without further ado, I will let Dan take this. If you have any questions, you may use the chat function so I can relay that question over to Dan. Thank you very much for your
Thanks, Pam. For today, I'm going to do a case study on a bridge here in Ohio. Many of you are familiar with it, and I'm going to try and talk about some of the different unique aspects of it and general design philosophies as I go that I've learned over the years. So get the most of you are familiar with for this the bridge is in Dublin, which is just outside of Columbus. Maybe most of you are aware, but those of you who aren't, the city of Dublin is situated right on the Scioto River. There is the historic part of Dublin, which is here on the west bank of the river, and that's been there quite a while. And the new part of Dublin, downtown Dublin, is being developed on the east bank of the river. And so the city has been trying to develop a walkable city. So the intent is to have a city where people can live, work, and go out and have entertainment all right here in the downtown area. And this new development on this bank has really been kind of divided by the Scioto River. The entire area is called the Bridge Street District, appropriately enough for this project. And the Bridge Street is currently, or was before this project, the main crossing of the river for the downtown area. So a sidewalk on that bridge was the way to get across the river to the newer developed side over here. So in order to kind of expand that walkability and create that atmosphere that the city wanted in the downtown area, they probably 10 years ago started developing a plan to put a pedestrian dedicated crossing across the river, and that's what this project was. So here is kind of that historic Bridge Street bridge that was the previous crossing with a sidewalk, and you kind of shared the path with traffic on a relatively narrow sidewalk. So it wasn't the most comfortable way of crossing. And this is kind of an image of the newer area on the other bank, which definitely kept that Bridge Street theme with these arch pedestrian crossings between buildings. So they really are making a big effort to keep people walkable city. So in order to further that, they got together with an architect. Indra Studios was the architect on this project. They put together a vision for the type of bridge they wanted, and really settled on a suspension bridge set right on the bank of the river here. And the part of the reason for the suspension bridge was to have a single element here in the middle, which was tall and visible from different parts of the city, and really created an icon. So the special attention was given to the aesthetics of that pylon. One of the things we're used to seeing on suspension bridges, you think of the Golden Gate or other suspension bridges, typically there's two pylons across the main span, and two planes of cables on either side of the deck. In this case, it's a single pylon and a single main cable. And we'll look at some of the implications and the results of that on the design of the bridge as we go through the presentation. So the presentation, kind of the agenda here, I'm going to start out going through the design phase and probably spend most of my time on the design aspect, go through the basic stats, talk about some of the features which are special and I guess differentiate this bridge from more conventional girder bridge design and construction. Talk about dynamics for quite a bit in the design phase and what considerations have to be made in the dynamics for cable supported bridges. We get into construction, and again, the item that differentiates this type of bridge from conventional construction is mostly the hangers, so and the cable system. And then at the end, I'll briefly touch on some of the aesthetic features of the bridge. Along the way, as I go through the presentation, I think I would like to just point out some of the rules of thumb and different kind of criteria and guidance that we use in designing unique features of bridges that I've either borrowed or developed along my years of designing unique bridges. So I'll point those out at different points along the way. So the bridge basics, here we see the plan and elevation of the bridge. We've got a main span length of 500 feet over the river. So the primary flow of the river is here, but the entire floodplain is this whole valley here. And then we've got 4 approach spans, 65 feet each. The pylon height is 160 feet above ordinary high water mark, and it puts it about 107 feet above the deck level. Typical suspension bridges have a pylon height in the order of 10 to 20% of the main span. So again, here's one of these rules of thumb that they use in the early design of the bridge and the preliminary phases. Cable stay bridges, the pylons tend to be a little higher, maybe 20-25%. On our particular bridge here, the pylon is, as I said, 107 feet above a 500-foot deck, which is a 21% of the main span length. And so that's on the tall side for a suspension bridge. But again, as we mentioned, the goal was to make this pylon visible from many parts of the city and really make it the icon and kind of the statement of the bridge. So the taller pylon was an intentional decision on this particular bridge. Talking about the superstructure, the basic design of the superstructure is a triangular steel box. That steel box is, for the most part, 10 feet wide. It's topped with a 14-foot wide concrete, cast-in-place concrete deck, so the clear width of the walking surface is 14 feet. The structure depth is 4 foot 10 inches. And again, talking about rules of thumb in general, for a cable supported bridge in general, your span to depth ratio is typically around 100, although this can vary significantly depending on different features. 100 is a good place to start with structured depth. And for our case, we're right in that range, the main span of 500 feet. Our structured depth is a span over 100. And probably familiar, most girder bridge designs, the span to depth ratio is right in the 20 to 25 range. So this obviously is much more slender, made possible by the support that the cables give the structure. The approach spans, it's a much more comfortable. We went with the same cross section for aesthetics. For the approaches, those are 65-foot spans, so the span to depth on those is a pretty comfortable 13. So we don't anticipate any difficulty getting those spans to work fairly well. Now a little bit about the pylon. So the pylon itself is also a fairly slender member. As you can see in the plan and profile there, it's made up of some pretty slender elements. And to try to get some guidance on how slender we can make this, we look at ASCE. ASCE limits the slenderness of steel primary compression members to a K/R ratio of less than 120. For this pylon is concrete, and they're a little less prescriptive about concrete elements. For concrete compression elements, they suggest that slenderness greater than about 100 has to be analyzed explicitly, but there's not very clear guidance on exactly what that means and what to do there. So looking at this, I've given the radius gyration of various portions of this pylon in general. Radius gyration is easy to calculate for circles and even for squares, but on this unique shape, it's a bit misleading potentially. But in the transverse direction, you can see the radius gyration. If I take the average radius gyration in the transverse direction on the height, I get a slenderness of about 118. But in this transverse direction, these curved elements are also very slender in themselves. So if we look at the slenderness of just those unique portions of the pylon right around the keyhole, those have a slenderness of about 110. And if you look in the other direction, you can see that this the radius gyration is more constant, and it's but it remains fairly slender. If I calculate the slenderness ratio in this direction, I get about 127. And although the radius gyration is easier to calculate in this direction, again, a rule of thumb for that, if you want to estimate, you can use 25 to 30% of the width in that direction as the radius of gyration. It generally gets you pretty close as an initial estimate. But the difficulty in this direction is calculating the K value. What is the K value in this equation? If you think about this as just a tall cantilever pylon, K value would be 2.0, which would make this very slender and probably not workable. It would be above 200. But we do have this main cable coming in, framing into the pylon here at the top, and you got to consider, is that generating, is it have the effect of a brace, or is it not a brace? And you kind of just have to use judgment on how much bracing the main cable actually provides to this pylon. If you considered it a fixed pin connection, as if it were a full brace, your K might be less than 1. In this case, I believe I calculated this with a K of 1.0. But regardless, we are above the 100 in any way you look at this. So that means we're going to look at slenderness explicitly. And for us, what that meant was nonlinear second order analysis, which includes the effects of geometric displacements on P delta effects. So we took a lot of time analyzing that in detail, looking at second order effects. In addition to that, we also did some detailed buckling analyses. We wanted to make sure that we weren't anywhere close to the buckling demand of this pylon. And again, in ASCE, there's not a whole lot of guidance given about how close to the buckling load you can get without exceeding the code. They just suggest that you look at it without a lot of guidance. And for my own personal evaluation on an element like this, I like to have a very comfortable margin of safety against buckling. At service demands, I like to be up at 20 or 30 times the buckling load, or have the buckling load be 20 or 30 times the service demand on the pylon, which puts you 10 or 15 times the demand at factored loads. But that's just kind of a comfort level with that. Again, I don't want to get anywhere near the case where I'm possibly buckling an element like this, which the whole bridge relies on. So we saw the configuration, and I mentioned earlier that we've got a single pylon and a single main cable, and the implications of that are that we've got a single plane of hangers, and we've attached those hangers to the inside edge of the girder, so that by doing that, the hangers are all inclined outward, leaving plenty of headroom over the deck and a nice open feeling on the deck. As we saw in plan, there's a S curve in the deck, and so the inside of curve on the other span turns to the other side. So we've got cables connected to the left side of the deck on the near span and the right side on the far span. So with these cables connected to one edge of the deck and inclined outward, we know that we've got a horizontal component of this cable force, which is carried by the deck as if it was an arch in plan view. So we've got arching action of the deck to handle this horizontal component of the load. And the vertical component of the load, of course, carries the dead load, but at an eccentricity, which generates a torsion. So the next thing we need to do is figure out how to handle this torsion and make sure that we are designing the bridge appropriately to carry this torsion in a stiff way that's not too flexible. So here we look at the torsion diagram for the main span. And you can see that on one span where the stays are on one side of the deck, the torsion is increasing. As soon as the stays switch over to the opposite side of the deck, the torsion is decreasing. Here at this end of the bridge, we've got a monolithic connection to a pier element, which allows the bridge to take out that torsion. The bridge is carried down to the ground by the stiffness of this pier. On the other end of the bridge, we've got an abutment. And so this abutment, typically on a bridge, is going to be a pinned abutment. It's going to be sitting on bearings, but we've got this triangular cross section, which doesn't lend itself well to bearings and supports. So we need to really, we'll get into how we handle that in a second. But the other thing about a bridge which is subjected to torsion like this is that we know that the torsion is not resisted well by individual girders. It really wants a closed path, a shear flow path. So again, I've got rules of thumb which I've developed over the years of dealing with these types of bridges that says that the enclosed area of your shear path resisting torsion really wants to be sized so that it's approximately equal. If you calculate it in the span length times the width of the bridge in feet squared, that's the enclosed area you want for your torsion resistance. So in this case, we've got a 250-foot span generating torsion, and it's 14 feet wide. So we want about a 3,500 square inch torsional area. In this case, we've got a triangle 120 by 56, so 3,360 square inches. We're pretty close. So I know in the initial design phase, I've got a pretty good stability chance of handling that torsion and being able to carry the load efficiently. So now let's look at what happens to this torsion once we get it to the abutment and try to take it out. Here's a view of that end abutment. You see the main span is here. This location here is where the expansion joint or the abutment would be, which is represented in the figure here. So what we did was we created a really wide outrigger beam here. We've made the beam much wider than this triangular steel box, and that allowed us to give a nice wide base to put the bearings, take out that torsion with a nice stable platform. So this outrigger beam here is actually 14 feet wide, so the eventual concrete deck will be the full width of this beam. But it gives us a nice stable platform to put these bearings on. The other thing that we notice here is on the extension of this bridge. Normally this would be a pin support, and most abutments are just a pin support, but in this case, most suspension bridges are continuous, and the span to depth ratios that we talked about, the L on 100 for a continuous is is really targeted at a continuous bridge. If we have a pin support here, that's going to make this span of the deck quite a bit more flexible. So we wanted to really find a way that we could make this abutment act as if it were a fixed support. And the way we did that was we extended the primary girder an extra 30 feet back into the abutment. So that's this extension of the girder. And then we put an extra bearing down here. This will be a tie-down bearing. It'll act to hold down the back point of the bridge and create a force couple, a 30-foot long moment arm to create a negative moment here at the port at the vent and generate the additional stiffness that will make this bridge deck act a lot better in its deflection behavior. So that's kind of a unique feature of this bridge. The other thing that's made this a little bit more challenging was that we also wanted, this is a 760-foot long bridge altogether, and we didn't want to lock in the temperature effects. So as the bridge heats and cools, the expansion joint here at this location, we wanted to make sure it was allowed to move. So these are sliding bearings. These bearings are allowed to slide, allows us to relieve the stress caused by those temperature strains. And so this abutment has a lot of unique features. And at the end, this entire area is going to be enclosed in a vault and not visible. So we didn't worry too much about the aesthetics of this piece, how it differs from the bridge, but we did spend a lot of time thinking about the behavior and how it will work in the bridge. So the next thing on cable supported bridges, I know most of us are bridge engineers, and you can't get through 4 years of civil engineering without seeing this video at least once. The Tacoma Narrows Bridge, and bottom line is cable supported bridges ever since this point had to consider dynamics from wind. So this bridge was no exception. We kind of worked with the RWDI wind experts in Canada. We had them build a scale model of the bridge in their wind tunnel for testing. And the model obviously has all the features of the bridge, the railings, it's got the triangular cross-section of the deck, even the ribs under the deck to really capture the wind performance of the bridge. In addition, probably the most key feature of the wind tunnel test is the setup in the stiffness. They've got springs back here in the connection of this to their wind tunnel that are scale models of the stiffness of the bridge that we gave them as input to their design of this model. So the structural model tells them what the stiffness, the frequencies of vibration are of the bridge, both vertically and also in torsion, because we know torsion on this bridge is a key feature. So this scale model is able to represent the accurate stiffness, weight, aerodynamic cross-section, and torsion behavior of the bridge. We went ahead and tested that, and we found that, in fact, this bridge does show some tendencies for vibrations. So this is the result of the wind tunnel. The wind blowing across there was generating vortex shedding in the bridge. So we needed to mitigate this, and we again worked with RWDI to figure out what was happening and how we could mitigate that. So in general, we've got this cross section, and it's triangular cross section was nice aesthetically, but not so good for structural and wind dynamics. And basically, what's going on is as the wind blows across, it comes across the peak of the bridge, and as it passes, it creates this vortex behind the bridge. That vortex pushes up on the bridge, and then the wind blows across the top surface when it's high and creates another vortex, which pushes it down. So these vortices alternate back and forth and create that oscillation that you saw in the video. So we came up with a scheme working with our wind testing partners and developed a wind bearing or a wind fairing or a guide vane that we attached to the bottom of the bridge in this shaped like a V. And the concept here is that as wind comes across the bridge, it gets pushed down the web, goes through the shape of the V, and is forced back up the backside of the web. and it creates a jet which blows out these vortices and really stabilizes the bridge because by eliminating the primary vortices that generates that oscillation. So we went ahead and tested that. We added the guide vane to the bottom of the bridge. You can see it down here attached to this section, and we reran the tests. So those first tests where we saw the vortex shedding behavior, and these are scaled deflections to the bridge scale. We saw more than 2 inches of oscillation was potential, and relatively moderate wind speeds of around 20 miles per hour. So that was before the wind guide vane was added. Once we added the guide vane, you can see the similar test, and that peak oscillation still exists, but it's greatly reduced. We got a reduction of that more than 4 times the reduction, and within our established criteria. So the wind vane was added to the design, and we moved on to the next phase. So going back to this figure we looked at earlier, and we talked about the depth to span ratio in the vertical direction of about 100, but we didn't talk about the transverse direction, and our depth to span ratio in the transverse direction is actually 36. And again, we mentioned typical girder bridges depth to span about 20 to 25. So this is actually quite slender in the transverse direction as well. And that's something that we definitely had to take into account and design for. And as I mentioned, the Tacoma Bridge was when kind of that moment where wind became a factor in cable-supported bridges. Well, the London Millennium Bridge is probably the point where lateral dynamics of pedestrian bridges really kind of changed its behavior. And in that study of that bridge, it was found that when people are walking across the bridge, you know, every time you step, there's a small lateral force that your foot imparts on the ground. And that lateral force, as more and more people come on the bridge, and the amount of people start pushing the bridge can start to vibrate in the lateral direction from that. And it turns out, based on those studies, that when that lateral vibration of the bridge in its first natural frequency gets to about 1% of gravity, then there's what they call a lock-in effect. And what that means basically is that as you're walking along the bridge and the bridge is moving, you tend to change your walking pattern, and you start to step in tune with the bridge to help you with your balance. As the bridge moves left, you kind of lean a little left, and vice versa. Well, that obviously exaggerates the problem, and it causes resonance. So once that locked-in effect happens, then resonance occurs and the vibrations can get out of control. And that's what happened in the bridge in London. So we went ahead and did some detailed stochastic analysis. We analyzed numerically different groups of people arriving and walking across the bridge, and over time. And we found that in our numeric analyses, when we got about 300 people on the bridge deck walking, the bridge vibration started to increase, and it reached that 1% threshold. And so we needed to figure out how to mitigate that. 300 people on this bridge is not very many. It's a pretty light, sparse crowd. We needed to increase that. The other thing we learned from studying the London Millennium Bridge was that this lock-in effect occurs with relatively sparse crowds, but once the crowd gets pretty heavy and dense, you might think that the effect is worse, but in reality, the walking and the movement of people is disrupted. You're not walking in your natural gait, you're not walking in your natural pace, and it's more randomized. And that occurs, the lock-in effect doesn't seem to be created once you get to past a level of service of about D, and I'll talk a little bit about what that means. Level of service for pedestrian is categorized in a lot of different sources and in slightly different ways, but in general, this is a pretty accurate, pretty consistent representation of that. The 300 people on the bridge that we had corresponds to somewhere around level of service AB. I think it's about 35 feet squared per person, where there's free flow, and that just wasn't enough. We certainly could expect that kind of crowd to exist on the bridge. So in order to get to a level of service D, we needed to get to somewhere between 10 and 15 feet squared per person. It's a much more crowded area. That represents approximately 800 people on the bridge of this scale. So we needed to find a way to get the bridge to be stable and lateral vibrations for on the order of 800 people. And what we looked at was the way buildings stabilize. It's not very common in bridge design to have lateral vibrations, but in buildings, usually skyscrapers, there is more of a tendency for lateral vibrations, and that industry has developed what they call a tuned mass damper, or a pendulum tuned mass damper more specifically. And the way it works is you've got a mass which is on the end of a pendulum, and we know we can tune the pendulum based on its length to match the frequency of the bridge. And based on that, you can see in these two figures that with the pendulum fixed, this vibration does not mitigate. In the one where the pendulum is free to rotate and dampen the bridge, it damps out very much quicker. So we applied this concept to the bridge, and this is essentially how it looks in our bridge. We didn't want some large unsightly thing attached to the outside of the bridge, so we wanted to do something that would fit inside the bridge and be completely hidden. And the way we did that was we essentially stacked a bunch of steel plates together, and we hung those steel plates on a lever arm or a pendulum here. So this weight is completely tucked inside the bridge, not visible from the outside, hanging from a pendulum. And this is the engineering drawing of it. Here, this big blue mass. As the bridge starts to vibrate laterally, this mass starts to swing, similar to what the image was, and it eventually damps out the movement. So we applied that to the bridge, and then recall this figure was what we had for the vibration of the bridge without the damping, and about 300 people, we exceeded this 1%. Once we added the damping to the numerical analysis, we see that we were able to easily get to the 100 without coming close to our 1% threshold. This is a logarithmic scale, so this is quite a bit below our 1% threshold, much closer to 0.1%. So we know that we successfully were able to design something to stabilize the bridge for the lateral vibrations. So I guess I'm going to transition now to the construction phase of the bridge, and talk a little bit about that. This bridge was delivered in the CMC method, which is not so common out here in Ohio. But I think it worked very well for this bridge. You know, the unique nature of this bridge allowed us, this method allowed us to get the contractor involved during the last phases of the design and really work out some of the details and constructability of the bridge. And you can see it here as the team. This is the owner's construction inspection rep, the contractor's construction engineer, and this is the contractor manager, the owner, and the cable supplier for the bridge. So the whole team kind of really worked together well, and I think allowed us to really develop a partnering atmosphere and deliver this bridge with as few problems as possible. But so I mentioned the cable contractor, and again, the element of the construction that differentiates this the most from conventional construction is these cables. So I'm going to spend a little time talking about the cables, and the cable system. So the cables are divided into, I'd say, 5 different categories here, and I'll just briefly talk about each of the ones. We've got the tie-down cable, and this cable really acts to anchor the main suspension force down into the ground. Then we've got the main suspension cable. This cable is about a 5-inch diameter, 4 3/4 inch diameter main cable, and altogether it's about 30,000 pounds. So it's a pretty significant heavy element. Then on a bridge like this, on a suspension bridge, quite often you've got connection at the tower. In our case, we did not want to touch the tower here. This was kind of an architectural aesthetic goal to just pass through the eye of the needle here. So these first 4 cables end up taking the bulk of the live load demand on them. So those first 4 cables are a little bit larger in diameter. There's 1 1/4 inch cables. The remaining typical hangers are 3/4 inch diameter. And then finally, we do have right at the pylon a restrainer cable, and that cable centers the deck in the hole in the pylon. Make sure that that deck stays right in the middle. It also stabilizes us a little bit for the wind loads and that lateral vibration from pedestrian live load that we talked about. So in general, the main guiding document for cables in cable supported bridges is the PTI guide spec unfortunately, that document is primarily written for highway or railroad bridges, and it really doesn't have a lot of details specific to pedestrian bridges. And mainly the difference here is the type of cables used. Here on this bridge, we've got a fully locked cable. This is a cross section of what that cable looks like. And in the center, it's fairly conventional. It's circular wires bundled together, in this case, in a spiral fashion around the core. But then these outer layers are what they call locked coil, and they're these kind of almost S-shaped fibers which lock together and give a really compact cross section. It prevents water from getting inside into the core of this cable. And you can see there's a lot more empty space here which water could get in, but these outer cables really lock that from happening. It also gives a nice aesthetic finish. Typically these cables are not covered in any kind of sheathing, so they are fully exposed, and those water tightness in it gives us an advantage in that regard. But as I mentioned, the PTI code doesn't really talk much about how to specify or test these cables and make sure they're fit for purpose. So we had to really develop our own criteria for this testing and kind of augment and borrow from the guide spec, but develop our own testing. So that testing system, I guess before I get that, the rule of thumb, if you're designing cable supported bridges and you need to get a quick estimate at the beginning, is you want the dead loads in the cables to be on the order of 40% of their strength. So that's a good way to get started on the size of these cables and get a good early estimate on it. So that's where we started, and it ended up pretty close to that number as well. But the testing criteria that we developed on most highway bridges or railroad bridges, the fatigue test on these elements really comes from either a truck tire or a railroad axle passing the location of a stay, creating an axial load spike in the stay, and as axles pass, then it gives a cyclic axial load. Well, in this bridge, in a pedestrian bridge, really the pedestrians don't generate that much of an axial load cycle in the bridge. There is a little bit, but it's not as significant on say a freight train bridge. But there is the tendency for these cables to have potential vibrations in the wind. So as the wind blows, the cables start to vibrate, and you can certainly build up a lot of lateral vibration cycles in these cables. So the test that we developed was that you would set these cables up in a testing bed put an axial load cycle by pulling with a piston axially on the cable, but in addition, at the midpoint of the cable, pushing it laterally to a certain amplitude and testing the vibration in that way. And we went to about 1 million, we did 2 million cycles on the hanger cables and 1 million cycles on the main cable. This video is a little choppy, not coming in very good, but you can kind of tell that the cable is moving laterally and axially at the same time. So we did this for the hanger cables. We did the similar test for the main cable. So now you see the main cables here. This is that 5-inch diameter main cable. We pushed it laterally. We pulled it longitudinally at the same time. We had a synchronized set of loading. And you can tell at this pace, 1 million cycles or 2 million cycles for the hangers is going to take quite a while. In fact, the hangers to get 2 million cycles took almost 2 weeks. The main cable cycles about a week. And we had to do this for multiple cables to make sure we had a good quality cable. So we were in this testing lab for months with these cables, and it was really a long lead time item that had to be planned for in advance. And the CMGC method really allowed us to engage the contractor early and advise them to start to address this as early as possible. Once the cables are tested and found fit for purpose, we need to figure out how to install the cables on the bridge. So the erection scheme that the contractor's erection engineer came up with was a little different than in our design concept. And the primarily difference was in these shoring towers. The design had these shoring towers, but the erection engineer decided to build them a little taller, and this bridge was erected about 13 inches above the final grade. And the reason for that was to bring the entire deck closer to the main cable, which made it a little bit easier to install these cable hangers. The distance between the main cable and the deck is a little bit less, and it's easier to pull these in. Even so, it did require quite a bit of force to bring this main cable close enough to install these hangers. See in this figure, all the hangers are attached at the main cable. It's hard to tell, but they're not quite attached at the bottom yet. They're just floating free at the bottom. And this is the step to actually install the first main hanger cable and get the pin installed at the bottom. So you can see some of the auxiliary equipment that was used to pull that main cable into place while they were inserting the pin in the hanger cable. Once the pin gets installed, then they also have to set the stress in those cables. And this is an element, you know, during design phase, we don't typically like to get into construction equipment or dictate means and methods to the contractor. But in certain cases, you just have to do it. You've got to think about constructability and access when you're designing. So we had put in our concept for a stressing device on the hangers, and the cable supplier actually did the installing and stressing. Came up with a very similar looking device. It essentially involves a couple of bottle jacks connected across the turnbuckle. So the idea is you stress this, you pull the cable closer to the pin and take all the load off this turnbuckle, and you twist this turnbuckle until you have the design length set at the gap in this turnbuckle, and then you read off the force in those cables and those bottle jacks, determine if you're at the correct desired design force at that stage of construction. And it worked very well. One of the lessons learned here is it's advisable. It's a bit time consuming to install this jacking device and get it on the cables and ready to go. Once it's on there, it only takes a few seconds to stress it, but installing it and getting it lined up is a time-consuming process. So having multiple ones of these, I would even suggest 2 or 3 of these or more, is going to be a time saver. You can have one crew actively working on one while another crew is removing the previous one and moving it to the next stage, get you ready to stress. So that's kind of one thing to think about in this type of procedure. Any of those long lead items, having spares. Finally, I'm going to just cover a few items on the aesthetics of the bridge. Anytime you've got a pedestrian bridge, the element that the public interacts with the most is going to be the railing, the hand railing here. And we did spend some extra time working on the aesthetics and detailing of the railing to make it come out, as nice as possible. So one feature, in the summertime here in Ohio, it gets pretty warm, so we wanted to have a wooden hand railing that would be a little cooler to the touch in the summer months, and we also wanted to minimize maintenance, so we went with a extremely durable, extremely hard Brazilian wood called Ipe for the hand railing element. It did take a long time to get a sustainable supply of this wood, so it's another long lead item that we identified as such, and made sure that the contractor was looking into getting this material on site early in the process. But I think it came out really nice, and it should be very sustainable with very minimal maintenance. It doesn't require painting or anything, so it should last quite a while. The other element, the longitudinal elements here, the cables, we use stainless steel, again, trying to minimize maintenance. As most of us know, bridges don't get near the detailed maintenance that, say, a building would, which has a maintenance crew. Bridges get, if they're lucky, 1 or 2 inspections a year with minimal maintenance. So we wanted to really make something that didn't require maintenance and would last in the weather out here. So the stainless steel worked well for that. And the last element I'll cover here is just talk about the lighting of the bridge. I went through a lot of iterations, but I think that the final lighting of the bridge came out very nice. It's fully programmable, so the city of Dublin has the ability to change the lighting scheme for different festivals. Here in this image, the pylon is set in blue and the cable's in red, so we've got this red, white, and blue theme. It can easily be changed through a dynamic program. In this image, it's completely set to red. And you can see here the finished railing came out very nice. I think it also has some lighting features involved, and you get a nice, comfortable light on the deck, as well as the aesthetic lighting on the features. So I think all in all, the lighting scheme came out very good. I think that I could go on for quite a while and talk more about all of the features, but I will kind of close it there. At the end here, I will show the time-lapse video of the construction of the bridge and open it up for questions while that's playing in the background. So if there are any questions, just let me know.
Thank you, Dan. We do have a question from Brooks. It's asking about the scale of the test model that was used in the point tunnel.
Yeah, I don't recall the scale exactly, but if I remember, I went up there and I think that the size of that model was, I want to say about 8 feet across, the length of it, and it might have been 2 feet wide, so 2 feet on 14, maybe a 1/8 scale model, something like that. But it was pretty good size. Time-lapse videos are always interesting to see the seasons change and the weather come through. Here's our last image of the red, white, and blue lighting scheme. Bridge open for business.
And here's another question. Is the presence of the dampers interfere with the access inside?
Yeah, we do have inspection access to the inside of the bridge. The dampers were placed, the 2 mast dampers were placed at the midpoint of each of these spans, and we included access openings through the web of the girder on each side of those dampers, and through the deck of the bridge we have a crawl space that workers would be able to get inside and then crawl along the length of the bridge. It's very small, as I mentioned. The total depth of the bridge is 4'10". It's tracked off the deck thickness, and you've only got 3 or 4 feet of clear space to crawl through there. So it's not comfortable, but you can get in there periodically, inspect the dampers, maintain the dampers, and also inspect the weld and the quality of the inside of the bridge, the paint. So we did provide, I think, a total of 4 access openings along the length of the bridge.
Here's another question. It says, why did tie-down cables go down from one side to the other side?
Let me go back to that question, that image I can find. So this is the location of that tie-down cable, and I think it's asking why it goes from, you can't tell here, but in plan view it goes from the left side of the deck, crosses under the deck to the right side. And the primary reason for that is, let me go to a plan view of the bridge. There we go. So in plan view, the curved deck means that the main cable is on the inside of the curve, and all of these hangers are pulling the deck towards the inside of that curve. And here you've got the main cable anchoring at the top of this column, and the this entire span of the deck is being pulled towards the inside. So the tie-down cable we took and we carried back across the bottom, underneath the deck, and anchored it on the opposite side of the deck so that we could balance the lateral load on this pier, pier 5 in this case. So the sum of these lateral components of the cable loads is balanced by the lateral component of this tie-down hanger. And then the axial component of the main cable is balanced by the axial component of this, so that we don't get a net longitudinal demand on the pier. At the same time, we don't get a net lateral demand on the pier. So really, we did that to balance all the loads.
Thank you. Was there any value engineering performed during this project, and if so, what were?
Yeah, in fact, there was. When we first were brought on board, the concept for this bridge was a bit different. There was, in fact, it was a longer main span. It was, I'm trying to remember, it might have been 600-foot main span, and it terminated here, and there was a very tall abutment placed just on the other side of this road. And one of the value engineering, probably the main value engineering concept was to shorten the main span to just the river span and primary the flood zone. And then we made these approach spans quite a bit shorter. So that saved quite a bit of money on not only could we lower the height of the pylon a little bit, we also shortened the length of the main cable used and shortened the overall, I guess, signature span. So that was the primary value engineering. There was a few other items as well, but that was probably the biggest item. It was short. Go ahead.
We do have more questions, but go ahead and finish, and I won't pass them.
Yeah, I was just going to say it shortened the main cable, and it made the diameter slightly smaller because we had less load on it.
Yeah, was the main cable assembled on site?
No, the main cable was prefabricated, and I kind of alluded to it, but I didn't get into a lot of detail on it. but the cable system is not like a conventional highway bridge. It is this locked coil system, and so this has to be prefabricated in a shop, and it's actually cut to length. These are what's known as fixed length cables, so it's very different than a highway bridge system where you typically have parallel wire strand for both the main cable and for the hangers. And with parallel wire strand, you have the advantage. You can basically take all the strands, lay them next to each other, pass them through a, something much like a post-tensioning anchorage. You pull them and then you cut off the excess length. In this case, the main cable and the hanger cables and the backstay cable had to be prefabricated, and they came from Italy, actually. The supplier was in northern Italy. They were prefabricated to a specified length. The end fittings were attached to the cables in the shop. So these fork attachments were connected to the cables in the shop. So the cable had to be cut to a fixed length and shipped out to the site and hung once they got out there.
Next question is, was the erection engineering performed by T.Y. Lin? If not, who provided this engineering service, and what were the discussions between the designer and the erection engineer?
We did do our own construction engineering, and we provided a construction engineering kind of construction sequence set of plans, but they were pretty rudimentary and they were not required. So the contractor also had their own construction engineer, which based out of New York. It was who was the construction engineer? SBP was this construction engineer out of New York. They're based in Germany, but the team was in New York. So they did their own construction engineering, and as I mentioned, they came up with a different erection scheme where they built the entire deck high, and then they lowered the fall. Once they got all the stays connected, then they lowered the false work, and that put the additional load into the system. But there was definitely a lot of interaction between our team and the construction engineering team. We modified our design model to match their erection sequence, and any of the interim stressing loads that they came up with for their modified erection sequence were checked by us in our model, and there was definitely a lot of back and forth, not only on geometry control, but stressing, sequence, constructability. It was a very collaborative kind of method of going, and I think the CMGC process really fostered that collaboration between the parts of the team.
What advantages and disadvantages did you get with an S-shaped deck, and who decided on the S-shaped deck?
So I'll start with the second part first. The S-shaped deck was selected by the architect prior to us getting on board. So as I mentioned, the city of Dublin had contracted with Endress Studios long before we were involved in the process and developed this concept. Partly the S-shaped deck had to do with the most convenient place for the starting and ending point of the bridge. There were key connection points on each end of the bridge, which were not necessarily in line with each other. I apologize if this is making anyone sick, flashing through these. But on this end of the bridge, there was a key pedestrian plaza that was going to be developed along the axis of a key street in the newly developed area. Over here on this end, there is a pedestrian plaza that was being developed simultaneously with the bridge. So they weren't necessarily aligned. We could have gone straight across, but I think the S-shaped alignment gave an aesthetic benefit. I think if you see the final photos, the S shape definitely gives it a character that's different than a straight bridge. But in addition, with that single plane of stays connected, you saw the advantage of the ability to connect to carry the torsional or the horizontal component of the anchor load in a arching effect in plan, and that is an advantage. It can be done without that, but really it does benefit the bridge from having that curve. But in short, it was primarily selected aesthetically.
Why did we come up with the triangular shape as opposed to the rectangular depth? And is this a fracture critical bridge?
Yeah, so the triangular girder shape, again, it was selected by the architect prior to our team coming on board. Triangular girder, we probably all recognize is not the most efficient structural shape. It was selected for aesthetics. They wanted the very sloping web, which gives the appearance of even more slenderness than original. We did introduce a bottom flange kind of hidden inside the box to carry some of the tension and compression in the positive and negative moment regions, just to carry it. So we really kind of ignored the bottom triangle in our design. We definitely had to look at it to see that it wasn't overstressed, but the primary structural flange was hidden inside the box, and it created kind of the traditional bottom flange. A rectangular shape certainly would have been more structurally efficient, but didn't have the aesthetic benefits. As far as fracture critical, yeah, the bridge does have fracture critical elements. Those were identified on the plan set as such, and detailed welding quality control plan was developed. This bridge was fabricated at a shop in Florida, and those fracture critical elements were inspected, to the higher standards that requires, as well as the details were developed to the fracture critical standards and identified on the plans as such.
And I think this is our last question. If the tie cable is below the flood level, how is the cable protected from damage due to debris, such as large trees hitting it and becoming lodged between the cap?
Yeah, so that's an interesting question, and I didn't cover that in the presentation, but it is in the floodplain here, and it's almost out, but it doesn't fully clear the 500-year floodplain or even the 100-year floodplain. So there is potential for debris and even stream flow to get to the location of that cable. So what we ended up doing was putting in a steel pipe protection on that cable, and so the bottom portion, all the way from the foundation up to above the 500-year flood level, is protected by a permanent steel pipe that the cable runs through, and that pipe doesn't prevent the debris from collecting there, but it protects the cable from being severed by any kind of debris that comes across there. So there is a steel pipe. The upper portion of the cable does not have the steel pipe, but we did need to put in a localized protection to keep that cable from being damaged in any way.
Thank you very much. Really a good presentation.
And what's the load rating of the bridge?
Load rating, I guess. Pedestrian bridge, it's a little bit different. You don't have a vehicle. We did design the bridge for an H10 truck, which is what ASCE requires for a bridge, a PED bridge of this width. It varies between an H5 and an H10 depending on width. At this width, an H10 vehicle was the governing vehicle. So you can drive a 10-ton truck across this bridge without any problem. You might have to navigate those S curves a little bit carefully in the pylon hole, but that's the largest vehicle we designed it for, and we kept in mind the potential maintenance vehicles that the City of Dublin had in their inventory, make sure that the choice of the H10 vehicle was appropriate for what's the likely vehicles that the city might put on.
Thanks again. Thank you very much for your presentation, your time. Thanks everyone for participating. Just a reminder, we will send the PDF certificates at the completion of the presentation next week of the seminar. And our next presentation will be on bridges in Columbus Crossroad, phase 4. It will be on June 1st, which is Monday next week at 11 a.m. Thank you very much again. Really appreciate your time, Dan.
Thank you.